Our cities are basically bleeding water through thousands of invisible wounds. We're talking about silent leaks, hidden deep underground, wasting one of our most precious resources. But what if we could hear them? Well, in this explainer, we're diving into a really cool study that trained an AI to do exactly that, to listen for the super quiet sound of a leak that no human ear could ever pick up. Okay, so to really get why this research is so important, you first have to understand the sheer scale of the problem. Take a look at this number. 17 billion Hong Kong dollars. That's the estimated cost of water just gone in Hong Kong in a little over a decade. And it's mostly due to these hidden leaks in aging pipes. It's a staggering amount of waste. And it's not like this is some old problem that's getting better. No way. It's actually getting worse. The most recent data shows water loss hitting a record high. Nearly 40% of the city's metered water just vanishes. And the source material points out that almost half of that loss comes from leaks in government pipes alone. This is a huge ongoing crisis happening right under our feet. So what we have is this invisible and incredibly expensive crisis. The old ways of finding leaks, sending crews out to look around or do pressure tests, it's slow, it costs a ton of money, and frankly, it often misses the small leaks that grow into big disasters. The bottom line is, we desperately need a better detective. And that's exactly where this research comes in, turning to AI to hunt for clues we can't see or hear. Now, what makes this study so valuable, especially for other researchers out there, isn't just that they got a great result. It's how they did it. They laid out this really clear, replicable blueprint for building and training their digital detective. So let's walk through exactly how they put this whole test together. So the first piece of the puzzle, the very ear of the operation, are these things called acoustic noise loggers. The easiest way to think about them is like super sensitive stethoscopes that you can clamp right onto a water pipe. They're pretty cheap, easy to put all over a city, and they just sit there 24/7 listening for that faint, steady hiss that a pressurized leak makes. And here it is, the 4-phase blueprint. First, they went out and collected thousands of actual sound recordings from pipes all over Hong Kong. Then they had to clean up that audio, get rid of all the background noise like traffic and construction. Third, and this is super important, they extracted specific features from the sound, kind of like its unique fingerprint. And finally, they took all that data and used it to train and test a whole bunch of different AI models. Now check this out, because the quality of their data is what makes this whole thing work. This wasn't recorded in some quiet, perfect lab. No, these 2,110 signals came from a live, noisy, chaotic city network. They had a mix of metal pipes, plastic pipes, big ones, small ones, all of it. And having that real-world messiness is exactly what makes the final AI so tough and so practical. All right, so once the data was ready, the researchers kicked off what you could basically call an AI bake-off. They took 7 different machine learning algorithms, each with its own way of thinking, and they just set them loose on the data to see which one would turn out to be the ultimate leak detective. And here are the contenders and how they did. We've got the whole spectrum here, from classics like decision trees and support vector machines, all the way to a more complex neural network. The table breaks down how each one did across a few key scores, but we're really going to zoom in on the big one, accuracy. And yeah, after that first round, 3 models just blew the rest out of the water. Random Forest took the top spot with almost 94% accuracy. But K-Nearest Neighbors was right on its heels, and the multi-layer perceptron wasn't far behind either. These 3 were the clear finalists in the competition. And this is where things get really clever. The researchers didn't just pick the #1 model and call it a day. They asked, hey, what if we combine the strengths of our top 3? They decided to create what's called an ensemble model, which basically lets the best performers vote on the answer. The hope was to build something even more accurate and reliable than any single one. This set the stage for one final showdown. In one corner, you have their custom-built ensemble model, trained specifically on the sounds of Hong Kong's pipes. And in the other corner, you have YAMNet, a really powerful, pre-trained audio AI from Google that's designed to recognize thousands of everyday sounds. This was the ultimate test, the specialist versus the generalist. And the winner, with an incredible 94.4% accuracy, was the custom ensemble model. It wasn't even close. YAMNet, that powerful generalist, could only manage about 53% accuracy. It's just a perfect example of how, for a really specific, noisy problem like this one, a specialized tool will always beat a general one. So why the huge difference in performance? Well, this quote from the paper just nails it. YAMNet knows what a dog barking or a car horn sounds like, but it was never trained for the unique chaos of a city water system. You know, all the different pipe materials, the constantly changing water pressure, the city noise. The specialist model, on the other hand, was trained in that exact environment. It knew precisely what to listen for. Okay, so the model works, we know that. But for science to advance, an AI that's just a black box isn't all that helpful. The researchers needed to pop the hood and figure out why it was working. They had to decode the AI's logic to understand what it was actually hearing that led to its decisions. It turns out the secret ingredient was something with a very long name. Mel-frequency septural coefficients, or MFCCs. Don't worry about the name. Just think of MFCCs as the unique sound print of an audio clip. See, a pressurized water leak makes a really structured, consistent sound, and MFCCs are amazing at capturing that specific signature and telling it apart from random noise. And they could prove it, which is the best part. Using a technique called SHAP analysis, the researchers looked inside the model's brain and confirmed that these MFCC features, that unique sound print of a leak, were by far the biggest clue the AI was using. So the model wasn't just guessing. It had learned to find and trust the single most reliable piece of evidence. So this study built an absolutely incredible foundation, but the work is far from over. One of the best parts of the paper is that it also lays out a really clear roadmap for the future. So for any researchers watching, this next part is for you. This is where we go from here. The roadmap has 4 clear phases. First, get this thing working with real-time data for continuous 24/7 monitoring. Second, use adaptive learning so the AI actually gets smarter on its own over time. Third, make the dataset even bigger. Add more cities, more pipe materials to make the model more universal. And finally, develop smaller, more efficient, lightweight models that can run on tiny, low-power devices right there on the pipe itself. All right, so let's just boil it all down. What are the key takeaways here? First, combining your best models into an ensemble is a seriously powerful strategy. Second, finding those domain-specific features, like the MFCC sound print, is absolutely make or break for getting high accuracy. Third, you've got to use messy, diverse, real-world data if you want to build a tool that actually works in the real world. And finally, this whole blueprint is a scalable foundation that could one day be used to monitor an entire city. This whole thing leaves us with a really fascinating final thought. This research proved that we can build an AI with a sense of hearing that's basically superhuman, able to find a huge problem that is completely invisible to us. And it just makes you wonder, if an AI can hear a silent water leak, what other invisible crises in our infrastructure, in our environment, maybe even in our own health, could it help us find next?